So in our next section, we're going to talk about the VLAN trunking, which again is used between multiple physical switches when we're trying to span the broadcast domains or span the VLANs between the devices. And there's going to be two different ways that we can do this based on the frame formatting. But typically, the links between the switches are going to be trunks. There are a couple other design cases where you may want to run trunking in the network. One is that if you're going from the switch to the router, and the router can run what's known as routing on a stick or a router on a stick, where it has multiple IP interfaces or multiple IP subnets, then based on the VLAN number that the switch is sending it, it can route between them based on that. We'll take a look at some examples of that later. And also from the switch to your end server, like if you're running VMware, for example, you can have multiple virtual machines that are on different VLAN numbers. And over the Ethernet link that you're using to physically connect into the switch network, you can run this trunking encapsulation. But the overall idea behind this is that when the Ethernet frames are sent between the switches, we need some additional encoding in order to carry the VLAN number. And this is what our trunking encapsulation does. Where the normal Ethernet header, if we were to look at the actual layer 2 packet format, it doesn't have a field to handle the VLAN number. This is what the two protocols, ISL for inter-switch link or 802.1q, are going to be used to accomplish. Now, the overall design goal of either of these protocols is the same, that we're just trying to encode the VLAN number. The main differences between them are that the first protocol, inter-switch link or ISL, is a Cisco proprietary implementation, where specifically it uses 30 bytes of encapsulation, and it doesn't modify the original frame. So it adds a new header onto the front of it, it adds a new trailer onto the end of it, which is the frame check sequence for error checking. So it's not changing what's going on inside the original frame. The 802.1q is an IEEE standard, which basically means that any vendor can implement it. There's recommendations on what the actual protocol format is supposed to look like. And this is a 4-byte tag or a 4-byte header. Since this is modifying the original frame, when .1q encapsulation happens, the frame check sequence that's at the end needs to be updated in order to calculate a new error check on the frame. But in either case, it's basically going to do the same thing. There is a document on Cisco's website that is the inter-switch link and 802.1q frame formats. If you were to search for this document, it shows you the specifics of what do the differences of them actually look like. Here we have the ISL header, then the original data frame followed by the frame check sequence. Most of the time, these level of details really aren't that important because we're not doing low-level layer 1 and layer 2 programming. This stuff is going to happen automatically behind the scenes. But if you do want to look at those details, you can see this document here, inter-switch link and IEEE 802.1q frame formats. For the first of them, the ISL, the key again is that this one is Cisco proprietary. It uses 30 bytes of encapsulation, where 26 go in the front and 4 go on the end. Where the 4-byte trailer, or basically the end of the frame, this is used for a frame check sequence, which is used for error checking, to make sure that when I send it across, that the device who's receiving it, nothing changed from a layer 1 point of view. The advantage of this was that ISL supported not only Ethernet, but trunking with token ring and with FDDI. Today's networks, that really doesn't matter, because we don't really have implementations of token ring in FDDI in new implementations. You may find some very corner case scenarios where you have some legacy protocols, like maybe IBM mainframe that's still running on token ring. But the vast majority of cases today are just going to be using Ethernet. For this reason, a lot of new versions of code in Cisco's iOS don't even support ISL. 802.1q, by far, this is the one that's more popular to implement now, because you can run it between anybody's implementation. You have a Cisco switch on one side, and you have a Netgear switch on the other side, or some other vendor. There's not going to be any problems with encoding the packets, because it's standard defined. Specifically, this uses a 4-byte tag value, which is a header but not a trailer. Specifically, this is added between the source and destination MAC address and what's known as the length and type, or type length fields. These values inside of the Ethernet frame tell the switch what is the next upper layer protocol? Like, is it IPv4 or is it IPv6? Where specifically the encoding for IPv4 uses an ether type value of 0 by 800, where other protocols like the address resolution protocol for IP uses a value of 0 by 806. Really, this level of detail, we're not really that concerned about it. Just inside the header, there is a way for the next protocol stack to figure out, is it for me or is it for someone else? So when the router receives packets in its Ethernet interface and sees that it's 0 by 800, it knows that it's supposed to go to the IP process. Or if it's going to 0 by 806, it knows that it needs to go to the ARP process from a software point of view. But since we're changing the header, since we're adding these new 4 bytes between the MAC address and the type length field, it means that the router or the switch needs to rebuild the trailer or the frame check sequence. 802.1q also supports what's known as the native VLAN, which is used for untagged packets that go across the interface. And essentially the idea behind this is that if we had VLAN 10 on one side of the network and we have VLAN 10 on the other side, when router 2 is trying to send a packet to router 1 or to router 3, when the frame is received in here, inside the Ethernet header, we're going to have the source MAC address, we're going to have the destination MAC address, then we're going to have the type and length fields. When switch 2 moves this frame to the outgoing interface, to the trunk link, it's going to add the tag value between these two fields, between the MAC addresses and between the type length. And this tag value is basically going to tell the other switch what's the VLAN number that it's supposed to be in. So this VLAN number is significant between the switches. If VLAN 10 on this side, if we want the CAM table to basically be the same one that's over here, we need to make sure that they agree on this number. Now for the native VLAN encapsulation, this basically means that there could be a VLAN number, like VLAN 1 by default is the native VLAN. This is used where a packet comes from VLAN 1 on this side, goes across the trunk link, but then does not get a .1q tag. The idea behind this is that if I receive a frame on a .1q trunk link and it doesn't have a tag, I'm going to assume that it's part of my native VLAN. So really the only thing that you need to keep in mind for this value, the native VLAN, is that it has to match on both sides of the link. Otherwise you can end up in strange designs where the hosts are supposed to be in the same VLAN and they end up to not be, or hosts are supposed to be in different VLANs and they end up in the same one, where basically traffic leaks from one broadcast domain to the other one if the switches don't agree on the VLAN number between them. You can see this on the command line if you were to look at the show interface switchboard. What is the native VLAN number? And this is going to be always 1 by default unless you change it for some reason. So you can change it, but most of the time you just leave it that. It's not going to matter. There's some corner case applications where maybe they need the VLAN number. Like if you're running, one case would be like the firewall services module on the Catalyst 6500 or some of the intrusion prevention systems for security. Sometimes they want this number to be tagged and not untagged, because it's basically a problem at the application level. But most of the time, like between the switches, the number's not going to matter. As long as they agree on it, then they can either tag the frames on normal VLANs and leave them untagged on the native VLAN, and it's going to work fine. Again, the only problem case you're going to run into is that if on one side I say that, if on this side I say my native VLAN is 10, and on this side I say my native VLAN is 1, when these frames are encapsulated, they get no tag. When switch 1 receives them, it thinks they're supposed to be part of VLAN 1. So the traffic ends up going to the wrong MAC address table or the wrong CAM table.
Can you give me a high-level look at what kind of traffic in current networks would use the native VLAN?
It's kind of used for like backwards compatibility for devices that didn't support the .1Q encapsulation. One of the things that the Cisco switches were able to do with it originally is to tunnel spanning tree over it. And it's not really needed in today's networks, but if you had a Cisco switch that connected to some other switch, like Bay Networks, and then eventually it comes out on the Cisco switch on the other side, one of the kind of legacy problems would be that if the Cisco switches supported the per VLAN spanning tree protocol, the Bay Network switch didn't support this because this is a Cisco-specific implementation, Cisco proprietary. So one thing that you could do is send this untagged across the switch in the middle, and it comes out on the other side, and it looks like these switches are directly connected. In today's networks, you don't really need it, though, because we'll see there's a replacement for this, which is the rapid spanning tree protocol and the multiple spanning tree protocol, which are the new enhancements to Cisco's custom version.
Would you still need that if you're using RPBST?
You just need to make sure that all the switches agree on what the native VLAN is, and then it'll work itself out. There's also a feature for this that is known as Q&Q, or sometimes as 802.1Q tunnels. The idea behind this is that a service provider network that is running Metro Ethernet can take traffic from one customer, add an additional VLAN tag on it, send it across their own Ethernet transport network, and then it comes out on the other side as a single tag where the customer's traffic is not changed as it goes through the network. The idea behind this is that you could have a topology that looks like this, where we have the service provider cloud in the middle, and they're attaching to the customer edge 1 and customer edge 2 as .1Q trunks. Then on the customer switches, if we have multiple VLANs, let's say we have VLAN 10 here and VLAN 10 here, but we also have VLAN 20 and VLAN 20. The idea is that I want to get this traffic to bridge over the service provider network. But it's probably likely that the service provider has some other customer that's also using VLAN numbers 10 and 20. So what you can do is take the Ethernet frame that comes from the customer edge switch, which is attaching to the service provider, but it's under the customer's maintenance. You take the original data packet that has this VLAN 10 tag on it, or the original data packet that has tag 20. You put a new tag on the outside, let's say 2000. This becomes what's known as the Metro tag, which is what the service provider uses this to get between the customer sites. So in the service provider networks, we have multiple Ethernet switches, switch 1 and switch 2, that somewhere along their paths, they're running .1Q trunking. Then they're able to switch the traffic based on the new Metro tag of 2000. But when the traffic comes out on the other side, it comes out as the original one that went in. So the VLAN number is maintained end to end between the customer sites. So essentially there's an arbitrary length that you can continue to add the tag values over and over and over, which allows the traffic to transparently tunnel over the service provider network, where from the customer's perspective, it looks like their switches are directly attached. Like if I went to customer edge 1 and said show CDP neighbors, it would appear that CE2 is directly attached on that link. So it's kind of like how an MPLS VPN would work from a layer 2 point of view, but you can do it with just Ethernet. And one of the limitations of ISL is that you cannot do this. Overall, you'll see that .1Q trunking is a lot more popular than ISL is, simply because you have interoperability between the vendors. And keep in mind that this type of encapsulation is only locally significant between the switches. So if I had a case where I have connections from switch 1 to switch 2, switch 2 to switch 3, and then I have some end hosts. I'm trying to get traffic from A to B. A is assigned to VLAN 10, and B is assigned to VLAN 10. But technically, I could configure the link between switch 1 and switch 2 as a .1Q trunk, and then configure the trunk between switch 2 and switch 3 as ISL. It's not really going to make a difference because the only thing I'm doing is just adding that number as the frame is moving between the links. So you don't necessarily have to choose one or the other. You can use both, as long as this side and this side agree that they're using .1Q. And likewise, that this side and this side agree that they're using ISL. So let's take a look at an example of this now, where previously we had router 1 and router 3 that were connected over VLAN 10, and switch 1 is using layer 2 switching to get the traffic between them. It means they're in the same broadcast domain, they're sharing the same MAC address table. When we went to switch 1 and we looked at the show MAC address table for VLAN 10, we saw that there were dynamic entries in here that were for router 1 and router 3's MAC addresses. So we're going to use the same logic, but now we're going to extend it between an additional switch. So on switch 2, this has physical connections that go to router 2 and to router 4. The first thing I'm going to do is set up router 2 and 4 to be added to this network. So router 2 on its Ethernet interface is going to have the address 10.0.0.2/24, as is router 4, same subnet. From the switch that is connecting them, switch 2 in this case, when we enable the interfaces, we should see these two log messages saying that there's nothing wrong with the layer 1 status, that's our link up message, and there's nothing wrong with the layer 2 status, the line protocol is up. If I were to look at the show interfaces status, we would see that basically everything on this switch is its default parameters. That all of the interfaces are assigned to VLAN 1. There's some links between the switches that have automatically negotiated as trunking. We'll talk about this in a second. But I can see that my port fast Ethernet 2 and my port fast Ethernet 4, at a minimum, it shows that they're connected. So there's nothing wrong with my layer 1 status, like there's no cabling problems. If I were to look at the show CDP neighbors, I see that router 2 and router 4 are attached. On my local interfaces, these are fast Ethernet 2 and fast Ethernet 4. Now at this point, with no other configuration on the switch, since these ports are defaulting to both be in VLAN 1, I should see that router 2 is able to send traffic to router 4. If we look at the show ARP, router 2 and 4 are directly going to know each other's IP address to MAC address association. If I were to send traffic to router 1, we would see that this traffic is not going to get through, because on this portion of the network here, this is VLAN 1. On this portion of the network, it's VLAN 10. So between the switches, this is not the same MAC address table, basically. This means that when router 2 is sending its ARP request going to that all broadcasts, even if the frame floods over to switch 1, Switch 1 is going to get this. It's not going to send the packet out that port, and it's not going to send it out this one, because they're in different MAC address tables. We have VLAN 10 on this side, we have VLAN 1 on this side. So the next thing I would need to do would be to change the assignment so that this is VLAN 10 on this side. And remember, there's going to be 2 steps to this. First thing I need to do is what? Is to create the VLAN. So I say VLAN 10, that's going to create it. Then at the interface level, we assign it with what command? Switchport. Switchport access VLAN is 10, where the default option for this is 1 on all of the ports. So I did this on Fast Ethernet 2, same thing on Fast Ethernet 4. Switchport access VLAN is 10. Now also, to make this output a little bit easier to read, what I'm going to do is change the MAC addresses on the routers so we know what addresses we're looking at instead of looking at those long hex strings. I can do this on the router's interface if I simply say MAC address, and then I'll give router 1. Let's see if I can do all zeros in a 1. There's a specific format that you need to conform to. Okay, so that's valid. So this will be router 1. Router 2 will just be all zeros and a 2. Router 3 will be all zeros and a 3. And router 4 is all zeros and a 4. Then on the switches, on switch 1 and switch 2, I'm going to delete the old entries that they had in the MAC address table. And I could do this by saying clear MAC address table, clear the dynamic entries from VLAN 10. Switch 2 is going to do the same thing. The end result of this is not going to change any of the traffic forwarding. The only thing it's going to do is make it a little bit easier for us to read the table that all zeros and a 1 is router 1.
Now can you do the show interface all that?
If we show interface Fast Ethernet 0/0 on router 1, what it's going to tell us is that the original address was this. This is the burned-in address, but this is the one that I changed it to. Normally, you wouldn't really need to do this for any valid design case, but you technically can if you wanted to.
In this scenario, if this were like an actual live environment and it was actually going out, what would the MAC address be shown externally?
If it went out of the VLAN, the MAC address would change when it goes out of the VLAN. It would change to the router's address. So the key is that for these addresses, they're supposed to be unique, but it really only matters that it's unique on a per VLAN basis. Because the MAC address is what is considered a link local address. It means that it's only used to communicate with someone who's on your directly attached segment or your local segment. When I try to route traffic to a different router and then move it out to some other portion of the network, the layer 2 header is going to change anyways. It's going to change so that the destination address is my default gateway. Then when the gateway routes the traffic, they're going to change the source MAC address to be theirs. So as long as this value is unique inside of VLAN 10, that's all that we really care about.
We want to do this on these route. We need to change all the MAC addresses of all the interfaces in the router, right?
You can change all of them if you want to. You don't necessarily have to. The only reason I'm doing this is that when we look at the result of the show MAC address table dynamic for VLAN 10, it's going to make a little bit clearer who's actually attached to which ports. Yeah. So from switch 1's perspective, this goes to router 1. This goes to router 3. On switch 2, if we do the same thing and show MAC address table for VLAN 10, it knows that on port Fast Ethernet 2, there's some host that has this address. On port 4, there's some hosts that have this address. If router 2 was to now try to reach the devices on the other switch, so if I send a ping that goes to router 1's address, when this frame is encapsulated over the trunk link, the switch is not going to change what is the source MAC address. The only thing it's doing is going to add between the source and the destination MAC and the type length value, it's going to add the VLAN number. It's going to add VLAN 10. When switch 1 receives this, it says it came in on a trunk link and it came from VLAN 10. It means that I should now take the interface number, Fast Ethernet 0/13, and in the MAC address table, I'm going to associate port 13 with the address 000000000002. And when a frame comes from router 4, I'm going to learn that on port 13 as well, that all zeros and then the 4 address. So the key is that switch 1 is going to know about every MAC address that's in VLAN 10 over here. And switch 2 needs to know about every MAC address that's in VLAN 10 over here. And this is one of the scalability limitations of the Ethernet network. That if the broadcast domain is very large, it means that each of the switches needs to maintain tons of MAC addresses in their tables.
And the same thing happens independently for each VLAN that's on the switch.
Correct. For each VLAN, it's independent. So you keep separate copies of the table that I don't care if I have all zeros and then a 2 in VLAN 10 and 20, because they're separate virtual networks.
Are there any protocols that might dynamically create a new MAC address, maybe a virtual MAC?
There are. We'll talk about those later. There's some protocols that the device uses multiple MAC addresses. One of the applications for that would be the first hop redundancy protocols, like HSRP or VRRP or GLBP. Has to do with the association of your default gateway to a MAC address, and we're going to talk about that in more detail tomorrow. The end result of this is what we should see, is that router 2 should be able to reach router 1. And then it should be able to reach router 3. Now I may have forgot to, did I actually assign the VLANs? I did assign them. What this means is that the switches didn't automatically form the trunk link. Physically, in this case, the switches are connected together with Fast Ethernet 0/13. Switch 1 in my rack is a 3560, as is switch 2. On the trunk link that is connecting them, they're going to be running a protocol that is known as the Dynamic Trunking Protocol, or DTP. They're going to try to automatically figure out that this is a trunk link versus an access port. And that's what the dynamic switch port mode does. On these devices, if we were to look at the show interface Fast Ethernet 0/13 switch port, it says that the mode of the interface is running in dynamic mode. The operational mode, or basically the result of the negotiation, was that the interface is in access mode. It could also be the result of trunking. It just depends, did the other device also run dynamic mode? So did it run the negotiation of trunking? And did someone actually initiate the trunking? So did the other switch ask me, do you want to form a trunk link? Or did I ask them, do you want to form a trunk link? For this particular version, these ports are running in dynamic auto mode, which means to listen for DTP, but not to send DTP. It means that if someone else is trying to start the trunk link, that's fine, but I'm not going to automatically start it. This would be the difference on the interface between the switch port mode dynamic desirable versus dynamic auto. And you'll see that different platforms have different defaults for this. This particular one is running in dynamic auto, which means since neither of the sides are starting the negotiation, they don't end up forming a trunk link. But most of the time in the network, you wouldn't really want this. You know what are the physical connections between your switches. I would say this is a trunk link and nothing else is. So it kind of tries to ease the management to make the network more plug and play. But it's at the sacrifice of security in the network, because if an end host wants to run trunking, the only thing they need to do is send the switch this DTP request. And we'll talk about this when we get to layer 2 security. Normally, you would not leave the network in this state, the dynamic auto state. Question?
Would the ping have worked if both of those ports were on VLAN 10 participating in it?
If the port between them was in VLAN 10, yes. Because in that case, we're treating it just as an access port, which means it's just a native member of the link. So you technically don't need trunking between the switches, but only if you're using only one VLAN. The key with trunking is that you can encode multiple numbers, because I'm going to assume that on my switch I probably have more than one VLAN number being used. But if I were to say switch port access VLAN is 10 on this side, and then on switch 2 do the same thing, when I look at the show interface fast Ethernet 13 switch port, it says now the access VLAN is 10. That's the assignment. Once the spanning tree protocol converges, and if we were to look at the show spanning tree for VLAN 10, what I want to see for this is that it changes to forwarding state. Right now it's in the learning state, which means it's trying to build the MAC address table. Eventually this is going to change to forwarding, and then I can send traffic. And on router 3, actually, that's unrelated. So let's try this now. On router 1, let's ping 10.0.0.2 and 10.0.0.4. We can see from the debug output, router 1 is still debugging the ARP process, the address resolution protocol. So it's sending a request saying that this is my IP address, this is my MAC address. The MAC address is all zeros and ones that I set. I'm trying to figure out what is the MAC address of this IP. Router 2 replies, says this is my MAC address. Router 1 should now put this into the ARP cache, and the layer 2 switches should now all agree where the host is located. So if we show MAC address table, look at the dynamic entries for VLAN 10, it says that the hosts 1 and 3 are connected on ports 1 and 3 respectively. But hosts 2 and 4, both of them are located on 13. So you can have multiple ports that have multiple MAC addresses, but you can only have one unique MAC address per CAM table. So if someone else assigned router 1's MAC address here, there's going to be a problem. So let's say I were to do this on router 2. If we went to, and we should see we have connectivity to 1, 3, and 4. If I were to go to the interface and say MAC address is all zeros and a 1, if I clear the ARP cache and send new requests, the switches are going to figure out that there's a problem. Then I now have the same MAC address on multiple ports, and they may generate a log message here. It's a MAC address flap notification. It says the MAC address moved from port 13 to 1. Normally this is an indication of one of two things. Either two devices have the same address, or there's some sort of loop in the layer 2 network where a packet went out and then it came back around. Usually, what is supposed to stop this, the loops in the network? Spanning tree protocol is going to stop that. So if you were looking at your syslog messages, this might be one that you would want to do a notification on. That if I start getting this message over and over and over, it could mean that there's a loop in the spanning tree network. And that can quickly take your layer 2 network down. Also, router 1 is generating an error message. It says it filtered out an ARP request that came from our own address. So it knows there's some sort of error in the network. But again, normally you wouldn't have this because the MAC addresses should be automatically assigned as unique values to begin with. So what we have now is basically just access ports that are spanning between the multiple physical switches, where these two ports are in access mode. This is access, as are these. And they're all assigned to the same VLAN number, VLAN 10. This would be the case if you take two unmanaged switches, like you have a Linksys switch, and you plug it into another one. Even though you're spanning the traffic between multiple switches, it's technically not a trunk link. Because unmanaged switches, they don't need to run trunking, they just have all of the ports in the same MAC address table. But in most designs, this wouldn't be what we want, because it now eliminates the case that if I add a new VLAN on switch 1, let's say I have router 5 here that's in VLAN 20, and I have router 6 over here that's in VLAN 20. I now have no way to encode these frames as they go across that link. I could put another physical interface between them and then assign this to VLAN 20. But as you could probably guess, it's not very scalable to do this. So this is what the trunking encapsulation was designed to solve. That I want the VLANs to span between multiple physical devices, so I need to add this number in the header as it's sent between the two of them. So let's change this then between the switches. What I would normally want to do is say on this port, the ultimate goal is to get it to be a trunk port and to get it to be where the switches agree on what the encapsulation is. That both sides run ISL or both sides run .1Q. We could set the trunking encapsulation with the switch port trunk encapsulation command. Normally that's set to negotiate, which means we're going to use that dynamic protocol to try to figure it out. If I were to say the encapsulation is manually ISL, I would also have to say that the switch port mode is trunking. This basically tells it to not worry about the negotiation of the link. So in most designs, you would have both of these commands at the same time. Choose the encapsulation and choose that trunking is on. So switch port trunk encapsulation is ISL. Switch port mode is trunk. Once we do this, if we look at the show interfaces trunk, this is going to show any of the interfaces locally that are running in trunking mode. Some of them here I didn't configure, like ports 16 to 21. These ones ran DTP, the dynamic trunking protocol, and they automatically negotiated ISL encapsulation. The reason why in this case that this worked is that on the other side, this connection here goes to switch 4, which is a 3550. The 3550 by default has the switch port mode dynamic desirable command on. Which is fine as long as we know that there's a difference between them and we know how to verify that. So you don't need to memorize what are all the different platforms and what are the defaults. As long as I know, how do I check to see what is the mode and are you running the negotiation? And again, we can see that by looking at the show interface switch port. So on the other switches, if I were to go to switch 3 and to switch 4, On switch 3, if I show interfaces trunk, it says that these 9 interfaces, numbers 13 to 21, these are running in desirable mode. And if I were to show interface fast Ethernet 13 trunk, or excuse me, interface switch port, it says the interface is running in desirable mode, which basically means to start the negotiation. The other side has dynamic auto, which means to listen for it but not to initiate it or not to start the negotiation. But as long as they agree that we're running the negotiation of trunking, then the end result, the operational mode there, ends up to be trunk.
But desirable prefers ISL always.
It prefers ISL first. So it's going to try to negotiate ISL. If that doesn't work, it'll try to negotiate .1Q. If that doesn't work, it'll fall back to access mode. So let's look at the end result of this now. We should see that between these two port 13s, on switch 2, if I were to say, show interfaces trunk, I should see that number 13 is trunking. The status is trunking. We can see the native VLAN is 1 by default. So if we were running .1Q encapsulation, it would mean if you took a layer 2 packet analysis here, like you ran a sniffer, and you looked at the actual frames going across the link, the ones inside of VLAN 1, they would not have the .1Q tag. Only any other VLAN besides 1 would get it. But the end result is the same. Since they both agree that the native VLAN is 1, the MAC address tables for VLAN 1 end up to be the same. Then for any other VLAN like 10, since we're encoding this on the link, I know that 10 on this side is supposed to be 10 on the other side. There's also a couple other key fields here.
Real quick, can we see the config you have on that 13 again?
So the interface is running ISL encapsulation. It's running in trunk mode. This here is redundant. This doesn't do anything now. So normally you would just remove that. No switch port access VLAN. Same thing is going to be on the other side. If we look at the show interface trunk, or more specifically the show interface fast Ethernet 0/13 trunk, a couple other key things I would want to know here. One of them is which VLANs am I going to allow to be sent on that interface? This would be if you want to basically do a filter to say that certain VLANs shouldn't forward over this interface. The next one, it says which ones are allowed plus active. This means which ones did I actually create? So in the VLAN database of switch 2, the only VLANs that are active are 1, which is there by default, and 10. Lastly, which VLANs are in the spanning tree forwarding state and not pruned? These are the ones that are actually being sent. Where typically you would see that if there's multiple trunk links between the switches, they would normally all agree on what are the allowed VLANs. The number of active VLANs would be the same. This actually controls, are you sending traffic or not? And we'll see a little bit later in more detail why you would need to know this portion of the output. If we were to change this to .1Q configuration, it's only one command where we would say what? The switch port trunk encapsulation is .1Q. You'll see that for Catalyst iOS platforms that do not support this command, it means they only run .1Q. If you say switch port trunk encapsulation and then put a question mark and it says unknown command, it means it only supports .1Q. A lot of the newer platforms are moving towards that way.
So So they're phasing out ISL?
phasing out ISL, because there's really no advantage of running it.
Will two auto desirable ports negotiate trunking?
Desirable and desirable will. So the combinations would be if we had switch 1 and switch 2 connected. You could have on and on. You could have desirable and auto. You could have desirable and desirable. You could have on and desirable, or you could have on and auto. And these two would be kind of special cases. We'll look at these next. Most commonly, you would have the first one, where you know it's a trunk link, just statically set it to be a trunk link. You don't really want the network to negotiate this.
Hey, Brian.
Question?
When you're using a port channel, why do you have to add the trunk configuration to both port channel and its physical interface?
We'll get to examples of that, but if the configuration of the member interfaces, which are the physical ports, if it doesn't match the channel configuration, the channel fails to set up. Because you can end up in a spanning tree loop where let's say you have two physical links, if this port spanning tree configuration doesn't match the other one, I could have a port go out on this link and then come back on the other one. So the switch tries to prevent that, just says the config has to be 100% equal, otherwise it won't allow the channel to work. So when we change this here, switch port trunk encapsulation .1q, if we were now to look at the show interface fast Ethernet 13 trunk, or just show interface trunk, that would show all of them. The difference is then going to be what's the encapsulation. In this case, it's in this case it's .1q, not ISL. The end result of it is going to be the same though. From the end host perspective, router 1 doesn't care, am I using an ISL trunk or am I using a .1q trunk to reach router 2? Because the VLAN number is not encoded inside of my frames. It's only encoded between the two switches. This means one of two things here, that 1 and 2 can't communicate with each other, either by changing that MAC address that I did before so that it would have the overlapping address, either that's still stuck in the MAC address table, or there's something wrong with the trunk link. If you have a problem with layer 2 communication, if the devices are supposed to be on the same VLAN and they're supposed to be on the same subnet, if you were to look at the show ARP, and it says the entry is incomplete, it means there's some error in the Ethernet network. So router 1 should be ARPing for 2, but it's not getting a response back in. From a troubleshooting point of view, probably the next thing I would want to check is there anything wrong with the physical cable between them? Now, previously we were sending traffic fine, so we know that shouldn't be an issue. But if we were to show IP interface brief, I would want to check, from router 1's point of view, is the link up and is the protocol status up? This first one shows the layer 1 status, second one shows the layer 2 status. I could then figure out who is my next hop neighbor that's connected to this port by looking at show CDP neighbors. It says I'm connected to switch 1. On switch 1, it's port fast Ethernet 0/1. If I were to go to switch 1 and say show interface fast Ethernet 1 switch port, this should show me any of the layer 2 options that I could possibly need to know. It says the interface is running in access mode. The access VLAN is 10. The next thing I would want to know is for VLAN 10, I know it's running between these two. But is VLAN 10 actually running between these two? because I should be getting the ARP request coming in here, and I should be able to flood it in that direction. So on switch 1, how could I check that VLAN 10 is actually running on that interface? If we look at the show VLAN, this is going to show just your access port assignments. So it shows that ports 1 and 3 are in access mode in the VLAN, but it doesn't show me my trunk links. Show interface trunk is going to show me on that port, is it trunking, and is the VLAN actually running? So all the way down towards the bottom, I need to make sure that 10 is in this category for spanning tree forwarding. And the switches actually should be generating a log message here. One is in ISL, one is in .1Q, where I probably entered the command twice on the same switch. But let's look at another thing here. Let's say show interfaces status. The switch should be detecting this, and it should say that the interface is in error disable mode. This version may not do that automatically, but we can see the result of it is that I cannot encode the frames over the trunk because the frame format on one side doesn't match the framing on the other side. So I need to make sure both of them are running the same encapsulation. So on switch 1 here, I would need to go to Fast Ethernet 13 and say what? Switch port trunk encapsulation is .1Q. Now when router 1 sends the ARP, eventually it should get the response back in. We'll see it's still going to take about 30 seconds here because spanning tree needs to go to the forwarding state first. Now I got the reply. So now eventually 1 and 2 should be able to talk, which they can. But these type of steps that I went through, this is the type of stuff you need to know for the troubleshooting exam. So when they show you an example of the network and it says you can't get from point A to point B, you need to know what are all the possible variations of what could be going wrong in the middle, and then how do I try to track that down.
So by changing the trunk encapsulation, you force spanning tree to reconverge, is that right?
It will automatically reconverge because what happened is that when I changed the encapsulation, it took the interface down, it took the line protocol status down, and then it brings it back up. This is when spanning tree is going to rerun. So if we look at the final configuration results of this, as long as the switches agree on what the encapsulation is, that the interface is running in trunking mode, and that this number is going to match on the ports, then the broadcast domain between these 4 devices, it should be the same, it should be end-to-end. Which means now we can use IP at layer 3 to automatically do the resolution to the layer 2 MAC addresses with ARP. But if ARP is broken, then anything above this is not going to work. None of the routing protocols, none of the applications. We need to always verify that the layer 2 LAN works first before anything else on top of it. Then here we have the show interface trunk and the show interfaces switch port. The bottom one is going to show you all of the details. The top one is kind of a summary of the main stuff that's important. For the .1Q configuration, it's going to be almost identical. You're changing this keyword. But the end result of that is going to be the same. That the hosts are in the same broadcast domain, and they should be able to reach each other.